So we talked about vapor pressure lowering being a colligative property. Colligative properties depend on the number of particles, not on what they are, number of solute particles. So if we look at a phase diagram, I believe this is the phase diagram for water. And what happens is when the vapor pressure, okay, so let's think about this. The boiling point of a liquid, so up here is where we're liquid at atmospheric pressure, where it's changing from a liquid to a gas, that's the boiling point of this liquid. The boiling point is the temperature where the vapor pressure is equal to the atmospheric pressure. So when we increase the vapor pressure, I'm sorry, blanking. I am blanking on this. When we add solute and we move the vapor pressure, we lower the vapor pressure, that causes the boiling point to increase. So the boiling point increases and the freezing point decreases. So this is called freezing point depression, boiling point elevation. It's awesome if you can understand why that happens, but most important is just remember that it happens. I used to have a hard time remembering. I knew that the boiling point and the freezing point changed, but I couldn't remember what direction. And so what I finally came up with is, so here's our pure solvent, and when we add a solute, it makes the boiling point higher and the freezing point lower. It moves that range out, so it stays a liquid over a wider range of temperatures. Boiling point goes up, freezing point goes down. So the freezing point depression is given by this equation, which is not a terribly difficult equation. Delta TF is the change in the freezing point. Now, yes, the freezing point is going down. This, in our pattern of final minus initial, this should be a negative number, but it's usually reported as a positive number. Sorry about that. I won't try to trick you on that one. This is the change in the freezing point. It is equal to the molality of the solution, that's moles solute per kilogram solvent, times a constant. And that constant will depend on the individual solvent. So here's a table giving normal freezing points and freezing point depression constants for some common solvents. So we see for water, the freezing point depression constant is 1.86, and the units here are degrees Celsius per molal, because you take that and you multiply by molality, and you get a temperature. In the next slide, I think we'll see that the boiling point also has a constant. It's the boiling point elevation constant. And then here are the normal boiling points. You should know the normal boiling point and freezing point for water. The rest of them would be provided, or you'd have an opportunity to look it up, and you definitely don't memorize any of these constants. Let's calculate the freezing point of a 2.6 molal aqueous sucrose solution. So the word aqueous tells us that this has water as the solvent. We're going to need the freezing point depression constant, so I'm going to go back here. It's 1.86. So Kf is 1.86 degrees Celsius per molal. The equation that we need is the change in the freezing point is equal to the molality times Kf. Well, here we're given the molality, 2.6 molal. So we plug that in, 2.6 molal times the freezing point depression constant, 1.86 degrees Celsius per molal. Those silly m's cancel out. .6 times 1.86. 4.836 degrees Celsius. That would have two significant figures. Is that the freezing point of the sugar solution? No. That's the change in the freezing point. So we have to take that change and combine it with the freezing point of the pure solvent. So water, pure water freezes at 0 degrees Celsius. The freezing point is going to go down because of the addition of the sugar. So we're going to subtract that number. And we're going to get negative 4.8 degrees Celsius. Any questions? What does a popsicle have in it besides water? Sugar. So what do you think the freezing point of the popsicle is? Is it 0 or something lower than 0? It's lower than 0. If you take a popsicle and pack it in ice, it's going to melt. It'll melt slowly, but it'll melt because the ice melts at 0 degrees Celsius and the popsicle melts at a lower temperature. And as we'll see on Wednesday, we're going to make ice cream. Ice cream has milk, which has dissolved proteins and fats and things in it, and we're going to put sugar in there too. And so the freezing point of the ice cream mixture is well below 0. That's why you can't just use ice to freeze ice cream. It won't freeze. We're going to throw a bunch of salt, sodium chloride, into the ice, and the temperature of the ice is going to go down, probably get it down to around minus 10 degrees. And then it'll freeze the ice cream. So the boiling point gets elevated. The equation here is the boiling point elevation. The change in the boiling point is equal to molality times the boiling point constant, elevation constant. So the reason that antifreeze is used in radiators of vehicles instead of water is exactly because of this boiling point elevation, freezing point depression. So I grew up in the Midwest where in the winter it regularly goes below the freezing point of water. And if you had pure water in your radiator, it would freeze solid and your radiator would burst and you'd be in trouble. Around here, especially in the summer, it can be 115 degrees outside, and then you're running your car and it's generating heat, and the function of the radiator and the radiator fluid is to cool your engine. So it's very easy for the water to get above the boiling point, and then the pressure release on your radiator cap lets the steam out, and that's when you see that car at the side of the road with all this steam coming out. Just a note for safety, if that happens to you, just wait. Just wait till the steam stops coming out. Don't even open the hood. And definitely don't take that cap off. It's not a good idea. It's very, very dangerous. What antifreeze does is it lowers the freezing point and raises the boiling point. So it's like double bonus here. So we get the boiling point of the water higher so that the water can get hotter and still not boil over. And we lower the freezing point so it doesn't freeze solid. So let's calculate a boiling point. Calculate the boiling point of a 3.6 molal aqueous sucrose solution. So again, a sugar water solution, different concentration. This is the boiling point, so we need to use the boiling point elevation constant, which is different. Here's the freezing point one. The boiling point one is smaller, 0.512. 0.512 degrees Celsius per molal. Now this is the beauty of units. So if you forget what that equation is, here we have a constant which would be given to you with its units. And it's degrees Celsius per molal. And so looking at units, you might think, well, hey, if I multiply by molality, I'm going to get a temperature. That's a good bet. That's how I got through physics. Okay, so the change in the boiling point is the molality times the boiling point elevation constant. So here our molality is 3.60 molal and 0.512 degrees Celsius per molal. Those guys cancel out. 3 3.6 times 0.512. 1.8432. That one's going to have 3 sig figs. Is that the boiling point? No, that's the change in the boiling point. So the boiling point of water is 100 degrees Celsius. Is it going to be 101.8 or should we subtract? Well, the boiling point goes up, right? So we have to add. So 100 degrees. The boiling point of water is, in theory, exactly 100 plus 1.8432